In this session, we're going to see about a process called partial fraction decomposition. And before we actually do it, let's see the principles on which it's based. Suppose I have two rational expressions that I want to add. Let's say I've got 3 over x plus 4 plus 7 over x minus 2. In order to add these, we would need common denominators. And so, let's go ahead and obtain common denominators by multiplying by appropriate factors. And by so doing, we get 3 times the quantity of x minus 2 plus 7 times the quantity of x plus 4 divided by what's our common denominator, x plus 4 times x minus 2. If we go ahead and bring this all the way home, I'm going to simplify the numerator and multiply the denominator. We end up with the single rational expression 10x plus 22 over x squared plus 2x minus 8. Based on your knowledge of fractions, this process should make sense. What we're going to do in this video is start with that ending rational expression we just came up with and come up with the fractions that were added to make what we have. In other words, we're going to turn a rational expression into its constituent partial fractions. Now the factors in the denominator are going to take different forms, and we're going to see how to handle those one by one through our examples, starting with find the partial fraction decomposition of the rational expression 4x over 2x squared plus 3x minus 2. The first thing I notice, and it's very important, is that the denominator can be factored. This is essential, if we look back at what we just did, to coming up with the partial fractions. We have to be able to factor a denominator. And so let's go ahead and factor that denominator. And we see that this denominator factors into 2x minus 1 times x plus 2. These are going to be the denominators of our partial fractions. And so I'm setting up those expressions. So I have a denominator of x minus 1 and a denominator of x plus 2, and it's going to be up to us to figure out the numerators. There is a systematic process, so don't worry, we're going to work our way through this one. And so I said that the factors in the denominator are going to take on different forms. Basically, there are going to be a couple of possibilities and then a couple of iterations of each possibility. In this case, we see that both denominators, 2x minus 1 and x plus 2, are linear. The two possibilities I just mentioned are they could be linear or quadratic. In this case, they're linear. Let's recall that a linear expression is a polynomial of degree 1. And when we decompose these fractions, we're going to decompose them into proper rational expressions, which means that the numerator is going to be a degree that's smaller than the denominator. Well, the factor in the denominator, that is. And so since the factors are linear in the denominator, the numerators are going to need to be constants, degree 0. We want generic constants, and so we're going to use variables. And the variables we're going to use in this context are going to be uppercase A and uppercase B. So we start off by writing A over 2x minus 1 plus b over x plus 2. And this is the first step in the partial fraction decomposition. Now what we're going to do is we're going to pretend that we're going to go ahead and add the expressions on the right-hand side. To do that, we would need to get common denominators, right? So we're going to multiply the first fraction by x plus 2 over x plus 2, and the second fraction by 2x minus 1 over 2x minus 1. And we end up with, on the right-hand side, a times the quantity of x plus 2 plus b times the quantity of 2x minus 1 over the common denominator of 2x minus 1 times x plus 2. If this is starting to feel like the recall that we just saw on the previous slide, it's because it's the exact same principle. This is the right-hand side, which was equal to the left-hand side, and so it still is. And so this equation actually becomes 4x over 2x squared plus 3x minus 2, our original expression, is equal to that combined fraction, a times the quantity of x plus 2 plus b times the quantity of 2x minus 1 divided by 2x minus 1 times x plus 2. Now here we have two fractions that are equal to each other, and because of the way we constructed this, we know that the denominators are equal to each other, which means that the numerators must be equal to each other, and so we write down that equation, which means that the numerator 4x on the left-hand side is equal to the numerator a times the quantity of x plus 2 plus b times the quantity of 2x minus 1, the right-hand side's numerator. Let's go ahead and simplify the expression on the right-hand side, and we now get 4x is equal to ax plus 2a plus 2bx minus b. I'm going to write the left-hand side in a weird way in just a moment, but first, on the right-hand side, what I want to do is I want to put like with like. So I have ax, and then a little while later I have 2bx. And so I actually want to write that as a plus 2b with the x factored out, and I have my reasons. And then we have 2a with no x, and a negative b with no x. And I'm going to go ahead and group those together, 2a minus b. Now that was equal to what's on the left-hand side, which is 4x. I'm actually going to write this as 4x plus 0, because that's the constant on the left-hand side. It's 0. The reason I'm doing this is because we're about to pair up like with like. Let me pause this discussion to talk about something else for a moment. Suppose we have a generic quadratic expression, 3x squared plus 2x plus 5. And we want to liken that to a quadratic expression, ax squared plus bx plus c. Let's say our reasons are that we want to use a quadratic formula. I could ask you, for 3x squared plus 2x plus 5, what's a? And you would tell me that a is 3. And if I asked you why, you'd say, well, because 3 is associated with x squared on the left, and a is associated with x squared on the right, and so a must be 3. Likewise, you would tell me that b is equal to 2 and c is equal to 5. And what you're doing is you're mentally putting like with like. I want to do the same thing with the equation that we have with the uppercase a and b. So on the left-hand side, I have 4 as a coefficient of x. And on the right-hand side, after grouping, we have a plus 2b as a coefficient of x. From this, we can get an equation. We know that a plus 2b must be equal to 4, thinking of this like with like business. On the left-hand side, we have a constant of 0. You see why I wrote it now, because I can associate that now with 2a minus b. In other words, we can get that 2a minus b is equal to 0 because the expression on the left-hand side originally didn't have a constant, and so it must have been 0. Folks, this right here is a system of equations. A plus 2b equals 4, and 2a minus b equals 0. That's why this is showing up when it is. This whole process is because it's an application of solving systems of equations. If you're wondering when you would ever use this, it's something that would be used in calculus. And if you're not going to take calculus, so what? Right now you're just understanding or learning more about the language of math. But that's just so you know where it would be used. Now let's go ahead and solve this system. As a matter of fact, what I want you to do is pause the video and solve the system for a and b. And what you should have gotten as a solution to this system is a is equal to 4/5 and b is equal to 8/5. Because of what we had originally written, a was a numerator of a fraction, b was a numerator of a fraction, we can now write the partial fraction decomposition. And putting this all together, we get that 4x over 2x squared plus 3x minus 2 is equal to 4/5 over 2x minus 1 plus 8/5 over x plus 2. In one of the only times where it's okay to submit complex fractions as your final answer. So let me go ahead and circle this equation because this is the form that the answer should take. Now I want to point something out. At the very, very beginning, we wrote down the first denominator of 2x minus 1 and the second denominator of x plus 2. Suppose those had been reversed. Then a would have been associated with a different denominator, likewise b. Which means that at the end of the day, which is about how long it takes to do these, a and b would have been reversed. But when we put it back together into the fraction decomposition, the numerator goes along with the denominator, and so everybody's answer would be the same, provided all the work is right, irrespective of the order in which the denominators had been originally written. So that's not a big deal. Your a may be different than my a just because of the ordering. But when we put it all back together, our answers would all match. So this is the process. We're going to see 3 more examples, and they highlight the different kinds of denominators that we could have. I told you there were, I don't remember what I said, but there are basically 2 kinds of denominators that we're going to look at, and then 2 iterations of each of those things. Let's look at our next example. Write the partial fraction decomposition of the rational expression 4x minus 1 over x minus 1 the quantity squared times x plus 2. Oh, joy and rapture. Look at this. It's already been factored for us. We don't have to worry about that. That's all right. We're going to have plenty of other stuff to worry about with this one. What we see here is that the factors are linear. But the first factor, the x plus 1 quantity squared, is a repeated linear. Now what's about to happen isn't really intuitive, so let's consider the fraction 3/4. 3/4 could be broken up into the sum of 1/2 and 1/4. Note that in 3/4 the denominator 4 is 2 squared. And note that in the sum we have 1/2, so we have a 2 plus 1/4, and that 4 in the denominator is again 2 squared. You see, when the 2 squared shows up, it's a repeated factor. And it could be expressed as a fraction that had a factor that was not repeated in 1/2, and then that factor that is repeated in 1/4. The punchline here is that when we have a repeated factor, such as x minus 1 the quantity squared, we need to write down a fraction that has x minus 1 as a denominator, and we need to write down another fraction that has x minus 1 the quantity squared as a denominator. We have to take into account the various powers that could show up. Folks, if this had been a cubed to begin with, we'd have to write down x minus 1 the quantity squared, and then x minus 1 the quantity cubed. We'd have to take care of all of the powers up to and including the one that we see. The other factor is x plus 2, and so we need a denominator of x plus 2. So just real quick to reiterate, if a factor is repeated, then repeat the factor, increasing the power each time, until you have the same power that showed up in the original denominator. Now, these factors, repeated or not, remember, we're linear. And so what we want is constant numerators. And so we're going to write down that it's a over x minus 1 plus b over x minus 1 the quantity squared plus c over x plus 2. And now we're going to play that game of combining the fractions by getting common denominators. Why don't you go ahead and write down the result of that. Pause the video and do that. Okay, I'm going to show you an intermediate step to make sure you are on the right track. For the first fraction, a over x minus 1, we were missing one factor of x minus 1 and a factor of x plus 2. And so we multiplied numerator and denominator by those two. For the second fraction, b over x minus 1 the quantity squared, we were simply missing the x plus 2. And so we multiplied numerator and denominator by that missing factor. And then in the third fraction, c over x plus 2, we were missing 2 factors of x minus 1, and so we multiply numerator and denominator by x minus 1 the quantity squared. That was to make sure you were on the right track. if we were going down the wrong road, then make sure you have this as your fraction, or as your fractions. And then now let's go ahead and combine the fractions on the right hand side, but let's hold off on multiplying. Don't multiply anything out just yet. Okay, yeah, not a lot for that step. What we have is 4x minus 1 over x minus 1 quantity squared times x plus 2, our original fraction, is equal to a times x minus 1 times x plus 2 plus b times x plus 2 plus c times x minus 1 the quantity squared, all over the common denominator x minus 1 the quantity squared times x plus 2. And once again, we have denominators that match, and so it must be the case that the numerators are equal. So we're going to write down that equation. And so we have 4x minus 1 is equal to a times x minus 1 times x plus 2 plus b times x plus 2 plus c times x minus 1 the quantity squared. Now what I'd like for you to do is rewrite this equation, but go ahead and multiply the right hand side and put like with like on the right hand side. So pause the video and do that. So after doing that, we have the equation 4x minus 1 is equal to a plus c times x squared plus a plus b minus 2c times x minus 2a plus 2b plus c. Now, on the left-hand side, there isn't an x squared, so I'm going to write this as 0 x squared plus, and then we have our 4x, and then we have our minus 1. And you can see I'm color coding this. What we have is that 0 must correspond to a plus c, and 4 must correspond to a plus b minus 2c, because those are the coefficients on x. And negative 1 must correspond with negative 2a plus 2b plus c, because those are the constants that don't have the variable x in their terms. And so here we now have this system. It's 3 variables and 3 equations, so it's something that's solvable. And in this particular case, sometimes it works out this way, there's a shortcut that we can take to get to our answer. Let's look at this equation that has the factors in it. 4x minus 1 is equal to a times the quantity of x minus 1 times x plus 2 plus b times x plus 2 plus c times the quantity of x minus 1 squared. Check this out. If we were to let x equal 1, then the factors that have x minus 1 would become 0. And if that were the case, then what we would have is 4 times 1 minus 1 on the left-hand side, which is 3, is equal to b times 3 on the right-hand side. That would give me directly, since 3 equals 3b, b is equal to 1. Now we're going to do a similar thing, but I'm going to use the next equation because it's getting a little bit convoluted up there. If we were to let x equal negative 2, then the factors of x plus 2 would become 0. That would zero out the terms that have a and b. A because of the x plus 2 factor, and also b because of the x plus 2 factor. So if x is negative 2, then the left-hand side becomes negative 9, and the right-hand side becomes 9c, which gives us directly that c is equal to negative 1. So what we're doing is we're picking numbers that zero out particular factors, and then cleaning up the mess, substituting those numbers that zero out the factors for x, and then writing down resulting equations, and we have directly now that b is 1 and c is negative 1. Well, we can put that into the system that we have. And so that first equation that said a plus c is equal to 0, now it says a minus 1 is equal to 0. Guess what? that gives me immediately that a is equal to 1. Folks, we have that a is 1, b is 1, and c is negative 1. We're actually done. We don't have to solve this system using conventional techniques. It's something that works sometimes. Let's go ahead and write down the answer to the partial fraction decomposition. We have 4x minus 1 over x minus 1 the quantity squared times x plus 2, our original fraction, is equal to 1 over x minus 1 plus 1 over x minus 1 the quantity squared plus negative 1 over x plus 2. That last you might sometimes see written as minus 1 over x plus 2. I truly couldn't care less in this case if you give me plus negative 1 over x plus 2. It's something you typically see, just like leaving those fractions up there in the numerator. Here's the answer. Now suppose you wanted to check and see that you were correct. What you could do is you could get common denominators on the right hand side, multiply by appropriate factors, combine like terms, and you should end up with the fraction that we started with that's on the left hand side. So far, our denominators have had factors that were linear. Even if it was repeated, it was a linear factor. In our next example, we have 3x minus 5 over x cubed minus 1. Same instructions. Notice x cubed minus 1 is a difference of cubes, and as such, we can factor it. X minus 1 times x squared plus x plus 1. Two factors, one of which is linear, and the other of which is quadratic. It's important to note that the quadratic is prime, and in this context what you see is it's referred to as an irreducible quadratic, but that just means it's prime. Since it can't be broken down any further, we're going to write this down as the sum of two fractions, a denominator being x minus 1 and the other denominator being x squared plus x plus 1. We want to write down proper rational expressions, and so on the right hand side for the x minus 1 we're going to put an a in the numerator, but notice that quadratic factor is degree 2. So what we actually want is a degree 1 numerator. We want it to be linear. And if you think about linear in terms of y equals mx plus b, that would be a good way to think of it. We aren't going to use m and b. We're actually going to use bx plus c, which is the most generic linear expression we can come up with. So, linear factors get constant numerators, just a single letter, a in this case. Quadratic factors that can't be reduced or factored any further end up with linear numerators, and so will look like bx plus c. Right now you may be thinking, wait a minute, in the previous slide we had a squared in the denominator and we set it up using a constant in the numerator. It wasn't irreducible, it was repeated. So the thing that was squared, x minus 1, was linear. Now we have a linear denominator and a quadratic denominator. What we want is the degree of the numerator to be only one less than the degree of the denominator. The rest of this is the same game as before. So what I want you to do is go ahead and multiply by appropriate factors, combine the fractions, simplify, put like with like, and then write down the system. It's a lot, but go ahead and pause the video and work your way through it, and give this a decent shot before you come back to the video. Okay, now if you didn't give that a decent shot, you might as well just, I don't know, stop watching or something. This is your education, right? Okay, so for the first fraction, a over x minus 1, we multiplied by x squared plus x plus 1 in the numerator and denominator. For the second fraction, bx plus c, we multiplied by x minus 1 in the numerator and denominator. For the first one, we ended up distributing the a. For the second one, we had to FOIL. The result is that we now have an equation where the numerators are equal to each other, and we have 3x minus 5 is equal to a plus b times x squared, right? We put like with like, plus a minus b plus c times x plus a minus c. Now on the left hand side, I'm going to do the same thing I did before. We're going to write down 0 x squared and write that down as plus 3x minus 5. And now we're going to write down the system of equations. Because 0 is the coefficient of x squared on the left and a plus b on the right, we have that a plus b is equal to 0. Because 3 is the coefficient of x on the left and a minus b plus c is the coefficient of x on the right, we have a minus b plus c is equal to 3. And then because negative 5 is the constant on the left-hand side, positive a minus c are the terms that don't have x on the right-hand side, we have that a minus c is equal to negative 5. This is the system that we would need to solve in order to write down the partial fraction decomposition. Go ahead and solve the system and then write down the partial fraction decomposition. Go ahead and pause the video and do that. So you should have gotten that a is negative 2/3, b is 2/3, and c is 13/3. And when we write down this partial fraction decomposition, we have that 3x minus 5 over x cubed minus 1 is equal to negative 2/3 over x minus 1 plus 2/3 x plus 13/3 over x squared plus x plus 1. Yeah, we have these complex fractions running all over the place. Sometimes I see these written as like negative 2 over 3 times the quantity of x minus 1, right? Putting the denominator of the fraction in the denominator. And then the other one would become 2x plus 13 divided by 3 times the quantity of x squared plus x plus 1. I don't know, you don't need to do that for me. I would be perfectly content with the one with the complex fractions. In any case, there we are. Last example, same instructions. Our fraction is 4x cubed minus 2x squared plus 7x minus 6 divided by 4x to the 4th plus 12x squared plus 9. Notice the denominator factors. Into 2x squared plus 3, the quantity squared. As a repeated factor, we should write down one denominator as 2x squared plus 3, and the other denominator as 2x squared plus 3, the quantity squared, right? Because that's what we do with repeated factors. And because the repeated factors are quadratic and cannot be factored, so we have irreducible quadratics, our numerators should be linear. And so the first numerator is going to be ax plus b, and the second numerator is going to be cx plus d. Just make sure we use different letters all the time. And it's going to be the same game as before. Common denominators on the right, like with like, match things up. Go ahead and pause the video, see what you can do with this. Okay, so we multiplied the first fraction, ax plus b over 2x squared plus 3, by 2x squared plus 3 in the numerator and denominator. FOIL the result of that multiplying, and then equate the numerators. Finally put like with like. What we end up with is 4x cubed minus 2x squared plus 7x minus 6 is equal to 2ax cubed plus 2bx squared plus 3a plus c times x plus 3b plus d. And these equating coefficients gives us the system that we're going to solve. 2a equals 4. That's the coefficients of x cubed. 2b equals negative 2. Those are the coefficients of x squared. 3a plus c is equal to 7. That's equating the coefficients of x. And 3b plus d is equal to negative 6. And those are the coefficients, the constant terms that have no variable x. And this is the system that we would solve, or that we will solve, to do this. Notice we have letters A, B, C, and D, 4 variables. We ended up with 4 equations. These things work out really nicely that way. Why don't you, if you haven't done so already, go ahead and solve the system and then write down the answer. I get A equals 2, B equals -1, C equals 1, and D equals -3. Oh hey, you remember that trick? Yeah, doesn't work this time. Like I said, it works only sometimes. Now, if we refer back to what we'd originally written for our, where the A, B, C, and D came from, then we can now write down the answer. So our original fraction, 4x cubed minus 2x squared plus 7x minus 6 all over 4x to the 4th plus 12x squared plus 9 equals 2x minus 1 over 2x squared plus 3 plus x minus 3 over 2x squared plus 3, the quantity squared. You want to check your answer? Add the fractions on the right. There it is. I want to make one more note. Now, suppose we had some fraction and the denominator turned out to be like x cubed times x squared plus 4, the quantity squared. Now, I don't care what the numerator is. It's just how we would write down the fractions. Because x cubed is repeated, let me make that shorter. Because x cubed is repeated and it's linear, we would have to write down a fraction with a denominator of x, and then one with x squared, and then one with x cubed. And then we'd have to deal with the x squared plus 4, the quantity squared. We'd have to have one that was x squared plus 4, and then we'd have to deal with that repeat. Right, so x squared plus 4, the quantity squared. We'd have 5 fractions. Because x is a linear factor that's repeated, all of the x squared, x cubed would have constant numerators, a, b, c in this case. Because x squared plus 4 is quadratic, we would end up doing dx plus e. And then for the second one, where it was the quadratic squared, we'd have fx plus g. Now this really is getting out of hand. At 7 variables, we'd have to have 7 equations to solve the system, but what I want to highlight is if we have a mix of stuff and factors are repeated, you handle them the same way you have in what you've seen in this video, which is now over.